Now we're talking about the universal quantifiers. We're not asking you to negate them, but it might be a good thing to include just in case. You know how Alex does, it'll randomly give you a hard question. For each row of bow ties, check the true statement, and it might be more than one true statement per row. We just have to check it out. All right, so if we look at the picture in the first row, every bow tie has polka dots or dots on them. So let's read the statements. At least one bow tie does not have polka dots. That's not true. All of these bow ties have polka dots. Some bow ties in the row have polka dots. Yeah, even though all of them do, that is some. No bow ties in the row have dots. That's not true. They all do. Next row. One has dots and three don't. At least one bow tie does not have dots. That's true. Because this one doesn't, and that one doesn't. And those three represent at least one. In fact, there are three. Next one. Some of the bow ties in the row have dots. Yeah, one of them does. Absolutely. One counts as some. And here, no bow ties in the row have dots. That is not true because you see it. There's that one right there that has dots. So that makes that one not true. Last one. At least one bow tie in the row does not have dots. That's true. All of them don't have dots. That's at least one. It's four of them. So don't be caught up by the semantics of a number. It said at least one. Yeah, four of them. Four is at least one. Two is at least one. One is at least one. So at least one means one or greater. Surprise. Next. Some of the bow ties in the row have dots. You see any dots here? Nope. No bow ties have dots. This is correct. See how these rows have two, that row has one, this column? It's not determined by anything except common sense. If these are still confusing, there'll probably only be one of them, if that many. Next. This tree is 91 inches tall. It must be a baby tree. How tall is that in feet and inches? Remember that 1 foot equals 12 inches. If you don't remember it, now you know. So if I've got 91 inches and I divide by 12, 12 will go into 91 7 times with 7 left over. Now, if you try to put this in your handy dandy calculator, notice how I didn't jump to the opportunity to use this, but 91 divided by 12 is going to give me a decimal. So many of us are so dependent on our technology that we would write this decimal down, 7.58333333. But that doesn't tell you anything, only the 7. It tells you that it goes into it 7 times. So if you wanted to use your technology, you could find out, well, what's 12 times 7? It's 84. You would take that 84 and subtract it from 91 and find out that there were 7 inches between that. So 7 feet, 7 inches. Tiny little tree. All right, now we're getting into set theory. Now, when we talk about sets, there are a lot of things that could come up. We could talk about cardinality, the number of elements in a set, the elements. We could talk about proper subsets and subsets. But right now, we're talking about equal and equivalent. So just as a reminder, two sets A and B are equal if they have the exact same elements. So if you had CAB and ABC in two separate sets, they are equal because they've got the same exact elements. Now, they're equivalent, which you would think equal and equivalent are the same in our world, but nope, not in the world of sets. Equivalent means that they've got the same number of elements. So one set A could be ABC, and set B could be 1, 2, 3, and they both have 3 elements, so they're equivalent. So let's investigate these 4 examples. A is the set of even numbers greater than 9 and less than 17. Let's take the time to write this out. Greater than 9 would be 10, 12, 14, and 16. 16 is the last one because it's got to be less than 17. Now notice, this is set A, and look at set B. See, they can put set A in words, but those words, once you interpret them, are the same as set B. These sets are both equivalent and equal. So newsflash, when sets are equal, they are automatically equivalent because they've got the same number of elements. All the elements in set A are in set B. They are equal and equivalent. Same exact elements, same number of elements. Here, A is 37, 38, 39. B is 53, 54, 55. These sets are not equal. They don't have the same elements, but they are equivalent. Equivalent but not equal. The number of elements in set A is 3. This little e means what is the cardinality of A? How many elements are in there? There are 3. The number of elements in set B is also 3. Equivalent, same number of elements in each set. All right, let's look at this next one here. A is a set of integers greater than 6 and less than 10. So that would be 7, 8, and 9. So the cardinality of this set is 3. The number of elements in set A is 3. All right, set B is a set of integers greater than 6. See, here we have an ending point. It's greater than 6, but it's less than 10, so it's right in between. And these are integers, not all the real numbers. So greater than 6, 7, 8, 9, 10, 11. I mean, I could go on. I'll just put these ellipses to let you know it does. And this set has an infinite number of items. There is no like cardinality that we could just count out because it's not finite. So this is neither equal or equivalent. They don't have the same elements. But you could say that there's a 7, there's an 8, and a 9, but there's also a 10 and 11 and all the way to infinity. And that's not in set A. It's got to be the same. Next one. A is F, H, J, and M. There are 4 elements. B is J, C, D, 3 elements. They are not equivalent. They don't have the same number of elements, and they are not equal. They don't have the same elements except for that J, but they got to have the exact same all the way. All right, let's talk about subsets. I took the time to type out all the subsets of set A. The subsets of set A include all of the combinations of 3 numbers, 2 numbers, 1 number all by itself, the set itself, and the empty set. And how do we figure out how many there are? You do not have to list them out. Let me repeat myself. Please don't list them out. You count how many elements are in the set. A has 4 elements in it. So to find the total number of subsets, you do 2 raised to the number of elements. 2 raised to the 4th power. 16 subsets. It's not hard to list them, and you could, but they didn't ask you to, so don't. The number of proper subsets is the number of subsets minus 1. So it's 15. Why? Because by definition, a set cannot be a proper subset of itself. Proper subsets are smaller than the original set. So the only set that is a subset that isn't a proper subset is the set itself. Take that to Jeopardy.